Good morning, physics. It's Mr. Norton here. And we got a couple of cold days. Stay safe, stay warm. And we're going to continue to give you a little information these next couple days, even though we're not meeting. And I'll post on Classroom a little more detail, and I already posted a little bit yesterday. Yesterday being Tuesday, today being Wednesday, the first cold day. Basically, we finished the problem solving for Chapter 11 this week, and review for quiz. I'll give you the, then review for quiz. And then Monday we'll go ahead and start electricity. And then Tuesday we will have our work and energy quiz. Okay? So that's the plan. And I will post on Classroom additional details. Okay, so you're going to get a couple of videos today, Wednesday. The first one is I'm going to lay out the basics to conservation of energy, and then in the next one I'll do a couple of specific problem-solving examples. Okay, so I'm going to try to keep them to about 10 minutes apiece. Okay, and then I would say in terms of work, come on, it's a cold day. 2 cold days, we're off, so, relax a little bit. However, I would encourage you, at least one of these days, spend 20 minutes watching these videos, and then, 20 minutes working on the problems, and over either split it up 20 minutes a day, or maybe 40 minutes for one of the days, and that will lead you into Friday's in-class review. You will be exactly where you need to be going into the review. Okay? So, relax, but do find time to do some physics. Here we go. Okay? Problem set 1, I'll post the answers today, but just as a quick review, here's some things you know. GPE is mgh. This was from problem set 1. KE is 1/2 mv squared. That's a lowercase v. That's just how I write it. Some people were confused by that. Units: kilogram, meters per second squared, and meters. We call that a joule. And it's energy here, so this should be joule as well. And you're going to have kilogram, meters per second squared. And if you look carefully, both of these are kilogram, meters squared, meter, per second squared. So everything checks out. Okay, this is what you do in problem set 1. Okay, now moving to problem set 2. All right, there's nothing new. Okay, the difference is that you're going to see both of these in one problem. Whereas in problem set 1, when you were solving a problem, it was either potential energy or kinetic energy, but not both together. Okay? Sometimes in problem set 2, okay, so I'm just going to give you kind of a general overview for the next few minutes, and then in another video I'll do some specifics, okay? In problem set 2, sometimes they will talk about a change in potential energy. You climb stairs or you lift something. What's the change in GPE? Well, that will be mg times the height change. Okay? But for all intents and purposes, lots of times you talk about starting at height equals 0. So if you change your height by 4 meters, where are you at? You're at 4 meters, right? And so the delta H is 4 meters. So mgh or mg delta H, just be aware of that. Sometimes they ask you how much work was done, because we know that in order to give something energy, you have to do work. So let's talk about force and displacement. Well, to lift a big old box, you're doing mg, and the displacement is h. So literally we see there that any work you do will change the energy of something. So if you do 47 joules of work, the potential energy change is 47 joules. None of this is like terribly crazy, okay? This is why the homework should be pretty doable. Okay, likewise, maybe you don't lift something, but you accelerate something. Likewise, work would be equal a kinetic energy change. So in this, in some other case, if you hit the gas and the engine does work and it does 400 joules of work, what was the kinetic energy change? Well, it was 400 joules. Okay? And lots of times there, the kinetic energy to start is 0. It starts from rest. So if there's 400 joules of work, the change in kinetic is 400, and so then the final would be 400 joules. Still nothing revolutionary there. Okay? Note, up to now in class, we've been talking about masses you were lifting with a pulley. And so in the pulley lab, you were typically looking at, maybe, less than a joule or so of energy. With your Hot Wheels car, right? In that lab, typical energies there were like maybe 0.16 joules, pretty small, okay? In the homework, you're going to deal with real cars and real coasters, and now all of a sudden you're going to be dealing with like hundreds of thousands of joules, because these things are a lot more massive, they go a lot faster, and they are at much greater heights than the stuff we've been dealing with in lab. So when you see these kinds of energies in the homework, don't freak out. Alright, continuing. Okay, not bad. Almost like we were doing a lecture in class. You probably should, if you don't have this stuff in your notes, this you should have in your notes. This kind of stuff is probably worth jotting down, so pause and replay as needed. Alright, now, couple more general things. We're going to make some connections between class, and what have we seen in class? You saw a big bowling ball pendulum do this. Okay? You saw a skateboarder on a half pipe doing this. Okay? Which, by the way, it should look just like a pendulum for you, except it's a kid on a ramp instead of a bowling ball on a rope. Okay, then you saw a Hot Wheels ramp like this. Even though all these systems, that's supposed to be a car, even though all these systems are different, they should be telling you the same story, right? As things move from high to low, and I don't care what the thing is, they speed up, which means they gain kinetic energy, which is absolutely at the expense of gravitational potential energy, and the total energy is conserved. Energy Skate Park, that handout nails it, right? If you're still foggy on this, go back and look at that PhET simulation, Energy Skate Park Basics. You have a handout. If you own that, you actually probably get most of energy conservation. Alright, that's it for this one. The next one we'll start to talk some numbers.